Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. For this question, we're told, based on the direction field of y dash equals xe to the negative 2x minus 2y, determine the behavior of y as x goes to infinity. And this question was sent through by the same student who sent in the last question I worked through, which was on a very similar topic of slope fields and working out the behavior of y as x goes to infinity. So if you haven't seen that question and my solution, it's worth taking a look because it deals with very similar concepts. Even though this question says based on the direction field as opposed to the slope field in the prior question, they're just different ways of explaining the same thing. So at the end of the day, we're still going to have to draw up a slope field and analyze it to come to our conclusion about what happens to y as x goes to infinity. So you don't want to get too caught up on this terminology of direction field. I'll just refer to it in this question as a slope field. Alright, so I'll draw up the differential equation we're dealing with. So here we've got y dash is equal to x e to the negative 2x minus 2y. And as before, we want to know what happens to y as x goes to infinity. Now, in particular for this question, the student kind of emphasized that they were struggling with actually drawing up the slope field. So they had a bit of trouble not only interpreting the slope field, but actually drawing it up in the first place. As I mentioned in the prior video, it can be quite a tedious task to draw up slope fields, because what you have to do is you kind of start with a table where you pick values of x, and then you pick values of y, and then you work out y dash using the differential equation given, and then you kind of draw up the directional lines to reflect what you're dealing with. As was the case before, I've gone on to Desmos to let it do the grunt work for me. So we'll be able to kind of analyze this slope field to come to our ultimate conclusion of what happens to y as x goes to infinity. But what I might do, just to help with the whole approach of filling out this table and drawing up the slope field, what I might do is just pick a handful of points and do the calculation just to help explain why this slope field does look the way it is. Because I think at the end of the day, it's a very simple mechanical process. So once you've seen it in action a few times, you kind of don't need to then go through the process of drawing up every single one. That would probably not be a good use of time. So what I might do is maybe I'll leave this here so we can kind of see it off to the side. And I might pick some points. So maybe we'll pick some x values. We're really concerned with x going to infinity, so positive values of x. So maybe I'll just say, well, let's look at x is 1, 2, 3, and 4. Maybe that's kind of 4 points should be enough to kind of get the gist of what to do. With the y values, I might just pick a bit of above and below, and maybe even on the x-axis. So maybe we'll go y is 0, y is negative 1, y is positive 1, and maybe y is negative 2. So here we're going to end up with 4 points that we can plot, and they will be, in terms of this slope field that we see here, we'll have x is 1, y is 0. So we're going to draw up this line here. X is 2, y is negative 1, so we'll see this here. X is 3, y is 1. And then x is 4, y is negative 2. So what I'll do is I'll do the calculation of y dash, and hopefully what we see is consistent with what Desmos has produced for us. And that way, hopefully you'll get a better feel for why the slope diagram looks like this, and then we'll do our analysis to decide what happens to y as x goes to infinity. So I'll just get my calculator going. So at the end of the day, all we have to do is plug in x and y into this differential equation here. So when x is 1 and y is 0, we would get 1 times e to the power of negative 2 times 1. And then from there we subtract 2 times y, which is 0 in this case. So we'll get 0.135 and so on, which is very close to 0. So you'd expect to see a positively sloped but very flat line. And at 1, 0, that is what we see. Positively sloped but quite flat. At x is 2, y is negative 1, we would get 2 times e to the negative 2 times 2. And then that would be minus 2 times y, which is negative 1 in this case. So the result there would be 2.037, which is positive and quite a bit steeper. So we should expect to see a kind of positively sloped line that's much steeper than this first one. And at 2, negative 1, that is what we see. It's a positively sloped line and steeper than what we had over here. At x equals 3, y equals 1, we will get 3 times e to the negative 2 times 3 minus 2 times y, which is 1, and we'll get negative 1.993, and that is kind of similar in magnitude to this, but just sloping the other way. So let's see if that's what we got with Desmos. So at 3, 1, yes, negatively sloping. And then the last one, hopefully by now you've got the idea. If x is 4 and y is negative 2, we get 4 times e to the negative 2 times 4 minus 2 times negative 2, and here we'll get 4.001, and again positively sloped and quite steep, steeper than what we had before, almost twice as steep, so really steep. And if we go 4, negative 2, that's what we get, positively sloped and quite steep. So hopefully just through that little exercise you can see how this slope diagram kind of is constructed. Again, it's not much of a value add to watch me do it for every single point, but hopefully just that handful of points gives you an idea of the technique. It is very simple. You're just plugging numbers into an equation. That equation just happens to be a differential equation, which means you need x's and y's. So from there, I mean, let's take a look at the slope field that we've got. I mean, if we're concerned with x going to infinity, we can see that coming from this area, the tangents are positive, and then they kind of flatten out as they get closer to 0. And the same from above, the tangents are negative, and they get flatter and flatter. And as you get closer and closer to y 0, the tangents get really quite flat. And so that kind of gives you the idea that the kind of curves you're going to see are going to kind of be asymptotic towards 0. So, I mean, they may even hit 0, I'm not sure. We haven't actually solved this. But what we can definitely say is that as x goes to infinity, y is going towards 0, because we can see that from both directions, from both below and above the x-axis, that's what's happening. As the values of x get bigger, the tangents are kind of flattening out towards 0. So that's kind of how you would interpret that. So hopefully that's been helpful. I mean, as I mentioned in the prior video, if you had to do this in an exam, you would hope that the differential equation given to you would be simple enough that with just a handful of points you could get the idea. Typically, if if the slope field required involves a lot of points, then you'd typically lean towards going to technology like Desmos or Wolfram Alpha to do the grunt work for you. You wouldn't want to spend hours kind of plugging in numbers just to kind of get this chart. Yeah, so hopefully that's all made sense. And if you did find that explanation helpful, please be sure to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, be sure to subscribe to my channel so that you can stay in the loop. All right, tick boom.